Good morning and welcome to this, the lecture number 30 of the course Stochastic Hydrology. In the previous lectures, we have been discussing about the intensity, duration, frequency relationships. That is the IDF relationships, which are essentially used for flood control designs, typically for urban flood drainage, etc., where you would like to pick up the design intensity associated with the return period and associated with a particular design duration. We also saw the methods by which we can construct the IDF relationships, and we considered an example of the Bangalore city rainfall, using which we construct the IDF relationships for for a given rainfall data series. Now, today's lecture we will take this discussion forward and then look at, once we look at what do we do with the design intensities that we have obtained from the IDF relationships. That is, we fix a return period based on the type of design that we would like to make, and then corresponding to that return period and for a given design duration, we pick the intensity of the rainfall from the IDF relationships. Remember, IDF relationships are obtained from use of extreme value distributions. Typically, the Gumbel's extreme value type 1 distribution is what we use in that. Now, starting with the intensities of the rainfall, we need to form what are called as the design hydrographs, which will give the distribution of the rainfall for the design duration. So, just do not lose sight of what we are doing. From the design duration, we went to the IDF relationship. For the given return period, we picked up the intensity of the rainfall. Now, we are coming back and then distributing that rainfall over the design duration, because the intensity that we picked is in fact the maximum intensity. So, how this maximum intensity of rainfall is distributed over the design duration is what we will look at now. So, this is the procedure by which we construct the design hydrographs. Most of you who would have gone through a basic course in hydrology will know the difference between hydrograph and hydrographs. So, hydrograph is the time distribution of the rainfall intensities, whereas hydrographs are the time distribution where they show the graph of discharge versus time. So, we will start with the IDF relationship and then look at how we obtain the design hydrographs corresponding to the design intensities, and these hydrographs in fact are used to construct the hydrographs, and from the hydrographs we obtain the design dimensions. So, the IDF curves, from the IDF curves we would now like to obtain the design precipitation hydrographs or design hydrographs from IDF relationship. As I mentioned, the hydrograph is typically, it shows the rainfall intensity on the y axis and the duration on the x axis. We use what is called as a alternating block method, which is one of the methods to obtain the hydrograph. So, this is a method for developing a design hydrograph from IDF curve or IDF relationship. IDF is intensity, duration, frequency relationship. It specifies the precipitation depth occurring in n successive time interval duration delta t each. So, let us say this is 10 minutes, this is 10 minutes, 10 minutes and so on. So, of equal intervals delta t, how the precipitation depth is distributed with respect to time, and this is the total duration of the rainfall event. So, we are talking about a storm of duration from this point to this point. Let us say it is of 1 hour duration, it is of 50 minutes duration and so on, and we have obtained the maximum intensity or the design intensity of the rainfall from the IDF relationship. How we distribute this across time for the duration of the rainfall is what we will see now, and the particular method we are discussing is called as the alternating block method. What we do in this is, we know the maximum intensity of rainfall. From the intensity, we get the precipitation depth corresponding to the duration T d. Let us say we get I into T d as the precipitation depth. I is intensity, which has millimeters per hour or millimeters per time, that is length per time is the units for that, and time T d is the time. So, as we are progressing in time, let us say this is 10-minute duration, 20-minute duration, 30-minute duration, etc. So, associated with these we get the depths, and then this depth we distribute in this time interval delta t. So, the precipitation that is occurring in this duration will be simply the precipitation at this time minus precipitation at this time. That is what we do here. Like this we get intervals of precipitation, that is in first 10 minutes there is a certain precipitation, in the next 10 minutes there is another certain precipitation, and so on. What we then do is, we arrange these precipitation depths such that the maximum precipitation depth occurs at the center of the total duration. You have the total duration, let us say of 1 hour, and then your delta t is of 10 minutes. So, 10 minutes, 20 minutes, 30 minutes, 40 minutes, etc., up to 60 minutes. We obtain the maximum precipitation by looking at the T d 2 and T d 1 and so on, and then we arrange the precipitation in such a manner that the maximum precipitation occurs at the center of the total rainfall duration. Let us say this is the total rainfall duration, and we first fix the maximum value at the center. Then on either side we pick up the values from the precipitation depths, and then put one value here, next value here, one value here, next value here, etc. Like this it keeps on decreasing in this direction, also keeps on decreasing in this direction. So, let us say this was 1 hour duration, 10 minutes, 20 minutes, 30 minutes, 30 minutes may be here, then 40 minutes, 50 minutes, 60 minutes, like this. We put the maximum value of the precipitation at the 30 minutes and then keep decreasing on this direction and on this direction. That is how we obtain the precipitation hydrograph, design hydrograph. So, let us look at one example to drive home this point, a very simple procedure, except that you do not forget that the basis for all of this is the design duration, and then from which we are picking up design intensity. So, let us look at a storm, a 2-hour storm in 10-minute increments for Bangalore city rainfall, which I have discussed earlier, and we will again use the same rainfall data with a 10-year return period. So, you have 10-minute intervals, and then it is a 2-hour storm. So, 120 minutes is the total duration of the storm, and then we have 10-year return period. Now, we will just use the formula, empirical formula. You can also pick this up from the IDF relationship that we derived in the previous lecture, corresponding to a 10-year return period and 10-minute 2-hour duration. So, 2-hour duration and associated with the 10-year return period, you can go up go to the IDF relationship and pick up the intensity. However, we will use this empirical relationship here, I is equal to k t to the power a divided by t plus b to the power n, as I discussed in the previous lecture. And for the Bangalore city, or the for the Bangalore city, they have given these constants. So, we will use those constants exactly the same way as we did in the previous class, and then obtain for t is equal to 10-year duration, t is equal to 10 minutes, and which is equal to 0.167 hours, 10 minutes is in hours. Remember, the t that we are using here should be in hours. So, we get an I of 13.251 centimeters per hour. So, in this case the units are centimeters per hour, because this is a empirical relationship. So, we must be always careful about the units that we are using. Now, starting with this intensity, what we do is, what is it that we did? We took 10-minute interval here, sorry, we took the 10-minute interval, and for this 10-minute duration we obtained the intensity here. So, this is 13.251 centimeters per hour is the intensity that is occurring in this duration. Similarly, for 10 minutes to 20 minutes again you obtain the intensity and so on. So, at every interval of 10 minutes duration you calculate the precipitation intensities. Now, the precipitation depth is obtained by simply taking intensity into duration. So, 13.251 centimeters multiplied by the 10-minute interval 0.167, which is 2.208. There is a point that you need to note now. Let us say when you go to 20 minutes duration, you will put this as 20, the duration will be 20 minutes, and it will not be uniformly distributed because there is a non-linear expression here, and therefore, you keep putting t is equal to 10 minutes first, 20 minutes, 30 minutes, etc. So, you keep getting the accumulated precipitation depths. From here you get the intensities, and then you start getting the accumulated precipitation depths, corresponding depths. So, you got for 10 minutes you got a precipitation depth of 2.208 centimeters. That means, the first 10 minutes the precipitation is 2.208. Now, we will go to t is equal to 20 minutes. That means, you have a for precipitation of 20 minutes you get 3.434 centimeters. When you use it for 20 minutes and then multiply it by the time duration, which is 20 minutes, you get a precipitation depth of 3.434, which means what? During the first 20 minutes the total rainfall is 3.434, but during the first 10 minutes already 2.208 has occurred, and therefore, the remaining 10 minutes you will get a rainfall of 1.226 centimeters. Like this, we keep on computing what is the incremental rainfall that occurs during every 10 minutes in this particular case. Once we get that, this is how we get. Let us say these are the intensities, 10-minute duration intensity is 13.25, 20 minute 10.3. How did we get this? This we get from the empirical relationship by putting duration is equal to 10 minutes, 20 minutes, 30 minutes, etc. So, T d is put like this, and then we obtain the intensities. Then corresponding to this intensity we start getting the cumulative depths. So, this is associated with the first 10 minutes, next 10 minutes, next 10 minutes, etc. So, these are the cumulative depths. From the cumulative depth we get the incremental depth, that means, during that 10 minutes what has happened. So, let us say 0 to 10 minutes what is the incremental depth. Now, this is 2.208, 1.226, this will be this minus this will be this minus this, and so on. Like this we keep getting incremental depth 4.699 minus 4.194, that is what you will get here, and so on. Like this you get the incremental depth. Once we get this, you look at the center point here, this is the center point, put the maximum value that has occurred at the center. So, essentially what we are doing is that this value you look, this value is the maximum that has occurred here in the incremental depth. So, put this at the center of the duration. Then the next value we pick up 1.226, you put it here. So, this is 1.226. The next smallest value, which is 0.760, you put it here, Like this, one by one you keep distributing on either side of the maximum value until you reach the end points of the duration. So, I repeat, the maximum value you put at the center and then keep distributing the remaining values in their decreasing order on either side of the maximum value, and this is how you get the hydrograph. So, for the first duration of 0 to 10 minutes, you will get a total precipitation of 0.069. As you can see, the rainfall in precipitation depth is slowly increasing. It reaches the maximum and then starts decreasing and reaches the minimum. So, that is how you obtain the design hydrograph. So, this particular method is called as the alternating block method. We are alternating, we are taking one value here, one value here, one next here and so on. So, it is called as the alternating block method, by far the simplest method of distributing the design intensity that you obtain from the IDF relationship. So, this is the hydrograph that you get. So, precipitation in centimeters on the y axis, time in minutes in the x axis. This is total duration is 2 hours. For the 2 hours at 60 minutes you get the maximum value, which is 2.208, and then you are distributing the values. So, essentially this is the design hydrograph that you will use corresponding to the design intensity of the rainfall. Okay. So, this is what we do with the IDF relationships. Let us just quickly recapitulate what is the significance of the IDF relationship, how we obtain, and then what is the use of the IDF relationship. IDF relationships are essentially formed based on the extreme value distributions, which means you are essentially looking at the maximum precipitation depth, maximum flood volumes or the peak flood discharges and so on. So, you are looking at maximum values. Now, these maximum values are used to construct the hydrographs by some procedure. You construct the hydrographs and then route the hydrographs through your channel systems or river systems, etc., to get hydrographs at various locations. So, any of your hydrologic designs essentially require the hydrographs which are obtained from the peak flows. Now, from the IDF relationships you do not get the flows, what you get is the design intensities of the rainfall. How did we get? We fix the duration, which is the design storm duration, corresponding to the design storm duration, corresponding to the return period, you pick up the intensity. Now, from the intensity of the rainfall, we also know now how to distribute the rainfall during the duration. Let us say that the storm duration was 1 hour and you picked up the intensity of 30 millimeters per hour or some such thing. Then you use the alternate block method and then construct the hydrograph. From the hydrograph you can move to hydrograph and so on. So, these once you know the hydrograph, how to construct the hydrograph, etc., are not within the scope of this course, stochastic hydrology. We are essentially looking at only how to use the probability concepts in hydrologic designs. So, we will leave that part aside, that will be covered in your basic hydrology courses. From the IDF relationship you get the peak intensities of the rainfall. From the peak intensities of the rainfall you know how to construct the design hydrographs. From the hydrographs you move on to hydrographs. Hydrographs you route through your channel networks and then get your design criteria using your regular routing procedures and so on. Now, we will come back to some of the topics that we discussed earlier. So, for the time being we will leave aside the IDF relationships. We have completed the portion on IDF relationship. Some time ago in some previous lectures, maybe lecture number 21st, 22nd, etc., we also discussed about dependent and independent variables in hydrology and then how to formulate the relationships between the two types of variables. For example, you may be considering runoff at a particular location, which is dependent on rainfall in the entire catchment. Now, we introduced the concept of linear regression at that time, where we build linear relationships between the dependent variable runoff in that case and the independent variable rainfall. So, typically we constructed equations of the type y is equal to Ax plus b, where x is the independent variable and y is the dependent variable. Y can be runoff at a location and x can be rainfall in the catchment. Now, that was a simple linear regression. Simple because there is only one independent variable and one dependent variable. Linear because we are fitting linear equations there. Now, in hydrology there are situations where the dependent variable depends not on one, but several independent variables. Let us look at the runoff itself. So, we were always talking about runoff having been dependent upon the rainfall, but runoff will also depend on, let us say you look at a situation where you are looking at runoff at a particular location. Let us say you are looking at a catchment here and then you are interested in the runoff at this location, and we were saying that the runoff will depend on the rainfall that is falling on this catchment. So, we use this as the dependent variable and this as the independent variable. It is known from your basic hydrology that the runoff will not only depend on the rainfall, it will also depend on what kind of soils that are there in terms of, let us say, antecedent moisture content. How much rainfall has already fallen and how much soil moisture exists, and what kind of vegetation is there, what kind of slope is there, and so on. So, and also on the evapotranspiration that takes place and so on. So, the runoff at this location, although simplistically we always relate it with only one variable x, and therefore, we were justified in using the linear regression, also the simple linear regression. Once we start looking at the details of it, we know that it not only depends on the rainfall, but it depends on several other variables. For example, it may depend on x 2 here, x 1 may be rainfall, x 2 may be soil moisture, and x 3 may be temperature in as much as it affects the evapotranspiration and so on. X 4 may be the slope of the catchment itself and so on. So, y does not depend only on one variable, but it depends on several variables. The concept of the simple linear regression that we introduced earlier, namely y is equal to a x plus b, this kind of equation, we now generalize and look at multiple linear regression, where the dependent variable y depends not on one, but on several variables x 1, x 2, x 3, etc. So, we may write y is equal to beta 1 x 1 plus beta 2 x 2, etc., beta p x p. There may be p variables on which the dependent variable is dependent on. So, these are the p independent variables. From the simple regression now, we are now graduating into multiple regression, where we are talking about p independent variables, but we still retain the linear structure of the regression equation. So, this is a linear expression y is equal to beta 1 x 1 plus etc., beta 1 to beta p are all constants, therefore, this becomes a linear equation. And therefore, we now introduce a multiple linear regression. Multiple because there are multiple independent variables, linear because it is a linear equation. So, that is what we will do now. So, we starting with this, now we will go to multiple linear regression. As I mentioned, you have a dependent variable and you have several independent variables. Now, we should use all these independent variables to model the independent variable at this location. This can be runoff at this location, which is dependent on several variables x 1, x 2, x 3, x 4 and so on. So, that is what we do. So, we develop a regression equation for y in terms of x 1, x 2, x 3, x 4 etc., up to x p. How did we do the linear regression? Just let us recapitulate. You had the observed data on x and y, and we wanted to fit a equation of this type yi is equal to a plus bxi, and we put a cap to yi to show that it is a predicted value. There are observed data xi and yi, let us say rainfall and runoff, both the observed data are there. So, this is observed data. From the observed data you want to fit a best fit line here like this and get a and b. So, your objective there was to obtain the parameters a and b. How did we do that? We formulated error, this is the observed value yi and this is the estimated value yi cap. So, the error is observed minus estimated. We consider the square errors and write it in terms of yi minus yi cap using yi cap expression a plus bxi and so on. So, we formulate this expression and then minimize this m, which is the sum of square errors with respect to the parameters a and b, and therefore, we differentiate this m with respect to a and differentiate this with respect to b and set it equal to 0 to get the values a and b. So, that is what we did in our linear regression. So, we differentiate with respect to a and differentiate with respect to b and get finally a and b. Essentially, the principle remains the same. Please look up your earlier lecture notes, slides, where we have discussed the simple linear regression. We have also discussed some examples on that. When we go to multiple linear regression, the principle still remains the same, except that we will start working with the matrices now, matrices and vectors. Y is the observed values. Let us say you are looking at runoff at a particular location and you have the observed series of runoff values, and then you have x1, x2, x3 etcetera. These are independent variables for which the observed values are available. Let us say x1 is rainfall, x2 is soil moisture, x3 is temperature and so on. So, all these variables which are the independent variables, for these variables also you have the observed data. Then you need to fix or estimate the parameters beta 1, beta 2 etcetera, beta p such that the errors between the observed values and the predicted values. Predicted values are predicted from the equation, linear equation. The error between the observed and the maximum and the predicted is minimized in some overall sense. That is where we consider the squared errors and so on. So, precisely what we did in the simple linear regression, we repeat it for the multiple linear regression. The principle remains the same, the mathematics also remains more or less the same. So, we write the general linear model for the multiple regression as y is equal to beta 1 x 1 plus beta 2 x 2 etcetera, beta p x p. x 1, x 2, x 3 etcetera, x p are the independent variables. Rainfall, soil moisture, although rainfall and soil moisture may be related, we will consider that how to handle such situations in next topic, where we are discussing how do we handle the correlated variables. Right now, we will assume that they are all uncorrelated. So, x 1, x 2, x 3 etcetera, these are all independent variables. Let us say rainfall, temperature, catchment characteristics in terms of vegetation and so on. The beta 1, beta 2 etcetera, bp up to beta p are the unknown parameters for this particular model. When we use this model to predict the dependent variable, we put a cap. So, we say that it is y cap, and when we use that without the cap, that is the observed values. So, we also have observed values for runoff and we also have observed values for x 1 which is rainfall, x 2 which is vegetation or let us say the catchment area, x 3 which is temperature and so on. So, we identify those particular independent variables which are influencing the dependent variable. We have the historical or the observed data on these variables. We also have the historical or the observed data on the dependent variable y. Now, our task is to estimate the coefficients beta 1, beta 2, beta p etcetera, beta up to beta p. For every variable here y beta 1, y x 1, x 2 etcetera, we have n observations available with us. Let us say a runoff at a particular location, we have for the last 30 years we have all the values available. Similarly, concurrent values of rainfall are available, concurrent values of catchment characteristics are available and so on. So, whatever are the independent variables, we have the observed values associated with the dependent variable. Now, from these observed values, then what we do is, because there are n observed values here, we let us write n equations here. So, y 1, y 2 etcetera y n. What do we mean by that? Y 1 may be the runoff during the first month of first year, y 2 may be runoff during second month of first year and so on. So, like this we may have, if you have 50 years of data, monthly data, we have 12 into 50 which is 600 values. So, n becomes 600. Corresponding to each of these values, we also have observed values on the independent variables. So, x 11 is the first value of the first variable, second value of the first variable, nth value of the first variable. Similarly, first value of the second variable, second value of the second variable, etcetera. Like this you have x 1 p up to x n p. Let us say you are looking at 50 years of observed runoff data, which means you had 600 values for monthly runoff, and x 11 is the first value of the first variable, which is rainfall, second value of the rainfall, and 600th value of the rainfall, and this is the first value of, let us say, temperature, second value of temperature and so on. Like this you get for different variables, you get these values, and therefore, you write n equations of this form. Now, what we need to do is, we want those p variables beta 1, beta 2 etcetera beta p using this set of equations that we have so formulated. Now, n must be at least equal to p. P is the number of parameters, which is generally much smaller compared to n. So, a general guideline is that n must be at least 3 to 4 times larger than p. Now, p is the number of parameters, you may be typically talking about 2 or 3 parameters in our hydrologic cases, whereas n is the number of data values, which can be which is generally significantly larger. We write it in a slightly more elegant form using the summation notation. So, we can write it as y I is equal to j is equal to 1 to p beta j x I j, that is the ith equation, we write it in this form, y I is equal to sigma j is equal to 1 to p beta j x I j. Then we use the matrix notation, because this will be comfortable for this notation. Also, converting the set of equations in the matrix form will be convenient for us to derive the expressions for the constants beta 1, beta 2 etcetera beta p. So, look at the matrix Y, we have n values. So, it is a column vector, y is equal to n into 1, it has n rows here, is equal to x. Each of the p variables has n values. So, x is a matrix of n by p size into beta, this is capital beta. So, I write it as b, which is a vector, which is a matrix. In this case, it is a row vector with, I am sorry, it is a column vector with p rows and 1 column. So, what do you get? You will get n into 1 here, y is equal to x into beta, and capital B denotes the beta vector. So, this is the expression that we use as the regression relationship. So, when we write it in the matrix form, in the long form y 1 to y n, this is a n by 1 matrix, 1 by n by 1 vector, and then you have n by p matrix and then p by 1 vector here. So, this is what we write. Remember, these are the observed values of the dependent variable, and these are the observed values for the independent variable, and these are the parameters beta 1, beta 2, etcetera, beta p. Now, when we use these equations, we obtain the predicted values. So, we also write the predicted values from the same equation y I is equal to beta j x I j summation j is equal to 1 to p. We write the predicted value as j is equal to 1 to p beta j x I j. That is, when we use the expression, we get the predicted value corresponding to that. So, there is a observed value and there is a predicted value, and therefore, the error is y I minus y I cap. So, this becomes the error for the ith value. Now, this is the error, and then we consider the sum of square errors. So, this when we write it in matrix notation, let us say I have this y as the observed values and my predicted value is x beta. So, x into b is a predicted value. So, I write this as y x beta cap, which is the estimated values, and then I take it as a transpose E dash E, because I am squaring it. So, E dash E is what I take. So, y minus x b cap dash y minus x b cap. Now, this is the observed value and x b is the predicted value. So, this is the sum of square errors now, all right. So, the sum of square errors I differentiate with respect to beta, the matrix beta now, and equate it to 0, and that we will get it as when I equate it to 0, this for all j is not necessary here. If I write it with respect to individual j's, then this is necessary. So, we are writing it in terms of the matrix notation. So, when I differentiate and equate it to 0, we get the expression from here minus 2 x prime into y minus x b cap. This must be equal to 0. So, this we write it as x dash y is equal to x dash x beta cap. So, this is what we get from the requirement that d by db sigma E I square is equal to 0. Sigma E I square is written in matrix form as shown. Now, look at this expression now, x dash y is equal to x dash x beta. We are interested in getting beta cap. So, from this I will write expressions for beta cap. To do that, what we will do is use this expression and then bring it to a slightly more convenient form by multiplying it with x dash x inverse on both sides. Why that? Because on this side I have x dash x. So, I will make it 1 by taking the inverse of that and multiplying it with this. So, x dash x inverse I will take, and then pre multiplying with x dash x inverse on both the sides, I get x dash x inverse x dash y is equal to x dash x inverse x dash x beta cap, from which I can write beta cap is equal to x dash x inverse x dash y. This capital B here indicates in fact that beta is a vector, and therefore, we are indicating this by B. Now, x dash x is a p by p matrix and its rank must be p for it to be inverted, because we are interested in x dash x inverse, and therefore, its rank must be p for the matrix to be inverted. So, x dash x matrix, when we write, this is x, which is n by p matrix, and we are getting a transpose of that, and this is original n by p matrix. We write it as I is equal to 1 summation x I square. When you multiply this, you will get it like this, x I 1 square and then x I 2, x I 1, etcetera. So, these are the terms that you get for x dash x. So, once you get x dash x matrix, you can obtain your beta, which is given by x dash x inverse x dash y. Recall that in our linear regression, we also obtained the best fit or the goodness of the fit for the line, that was given by the R square, which is the sum of square errors due to regression and sum of square errors about the mean. So, that is what you get in multiple regression also. So, we define sum of squares of errors. So, we define R square as b dash x dash y minus, this can be shown to be this expression b dash x dash y minus n y bar square, where y bar is the mean of the y data and x dash y is what we have computed already, x dash y is what we would have computed here, and we get y cap, which is y bar, which is the mean of the observed data. Y is n by 1 matrix. So, you get n by 1 column vector and you will get y bar from that, and y dash y is simply y square, you are squaring the matrix and then you get this value. Now, this is a scalar number. So, R square you will get it as let us say 0.8, 0.9 and so on. So, this is a scalar number. So, when you do this, it will indicate the goodness of fit in some sense. The higher the R square value, the better is the fit using those parameters. So, we know now how to estimate beta cap, which is the set of parameters, and we know how to estimate the goodness of fit in terms of the R square values. So, this completes the expressions for multiple linear regression. So, multiple linear regression we use when there are multiple independent variables all affecting the single dependent variable. So, you have a single dependent variable y and then x 1, x 2 etcetera x p as independent variables. We have the expression y I is equal to or y cap is equal to beta 1 x 1 1 plus beta 2 x 1 2 and so on, x 2 1 and so on. Like this we formulate the expressions and then estimate beta 1, beta 2 etcetera up to beta p. To understand this better, we will just solve a simple example here. We will take only two independent variables and this can be generalized for any p number of independent variables. We look at the mean annual flood in a particular watershed. What I mean by that is that let us say we have collected data from several watersheds on the maximum discharge that has occurred over few years. We are picking up the maximum discharge and then we want to relate it with the area of the watershed and the rainfall. Remember, these are different watersheds and these are the rainfall that have caused this discharges in these particular watersheds. For example, a 43 centimeter rainfall occurring in a area of 324 hectares in a watershed of 324 hectares has caused a peak discharge of 0.44 cubic meters per second and so on. So, these are the interpretations. So, these are different watersheds. We are trying to relate the discharge, peak discharge with area of watershed and rainfall in centimeters. So, these two are independent variables, rainfall and the area are independent variables and the peak discharge is the dependent variable. So, we formulate the expression q is equal to beta 1 plus beta 2 a plus beta 3 r, where a is my area in hectares and q I will represent it as r, that is the discharge. So, this can be annual, I am sorry, q is the dependent variable and a and r are independent variables. So, I will express q as a function of a and r. To obtain a intercept, we make the first variable as 1. That means, we wrote in our long form as beta 1 x 1 plus beta 2 x 2 etcetera. If you make x 1 as 1, which means for all the n values you put x 1 as 1, then you get the intercept associated with the first variable, and that variable is beta 1, that parameter will be beta 1. So, we get q is equal to beta 1 plus beta 2 a plus beta 3 r. Now, the task is to obtain the values beta 1, beta 2, beta 3. So, we will express this in our usual notation as y as the dependent variable and x as independent variable matrix, and then beta, this is a capital beta. So, b as the parameter vector. So, we have these values now, these are the observed values. So, this is y and this is x 1 and this is x 2. So, that is what we write here. These are the observed values of y, and as I said, the first variable will make it as 1. We are writing essentially in terms of 3 variables now. The first variable we make it as 1, so that we get beta 1 as the intercept itself, and these are the second variable, which is area in this case, and this is the third variable, which is the rainfall. So, we are writing y is equal to x into beta. This is 12 by 1 and this is 12 by 3 and this is 3 by 1 size of those matrices. So, you look at this expression now, we need to get x dash x inverse x dash y. So, first let us get independently all these variables, all these matrices. So, we get x dash x inverse x dash y. So, x dash x is, as I mentioned, this is sigma x I square I 1 square. When you do this multiplication, you can write it in this summation form. We use these summations. This is I is equal to 1 to n of the first variable, I is equal to 1 to n, and then you are multiplying here the second variable and the first variable. I is equal to 1 to n, you are multiplying here third variable and the first variable, and so on. So, like this you get the summations. You can use any of the spreadsheet programs to obtain these, and you get x dash x matrix. So, for this particular case, you get the values x dash x as 12, 5, 2, 7, 7 and so on. Then we take the inverse, x dash x inverse. You can use MATLAB program for this and then get the inverse of that. So, this is x dash x inverse. From this you obtain this. Then you get x dash y, similar to what we obtained for x dash x. You can express this in terms of the summations. So, x dash y will be obtained as summation I is equal to 1 to n y I and so on, like this. So, the x dash y in this case turns out to be 8.06, 10642 and 417. Once you get both x dash x inverse as well as x dash y, you get b cap, which is a your parameter vector. So, the parameter vector is obtained by, this is x dash x inverse, which we obtained just now. This is x dash x inverse, this matrix, and x dash y, this is x dash y. So, this is 3 by 3 matrix, this is 3 by 1 matrix. So, you get a 3 by 1 matrix. So, beta cap is obtained as 0.0351, 0.0014 and this 10 to the power minus 5, 5.0135 into 10 to the power minus 5, which means this is the beta 1, beta 2 and this is beta 3. So, the expression that we can write in terms of our q, a and r is q is equal to beta 1 plus beta 2 into a plus beta 3 into r. R is the rainfall, a is the area in hectares. So, from this expression we can estimate q for any given a and r. So, let us look at how these values look, that is using this expression. Now, I want to examine what kind of errors we are getting and so on individually. Although remember, when we apply the regression equations, we are interested in overall error, and that is why we are looking at the maximum fit, which minimizes the sum of squared errors. but let us also apply this equation for the actual data and then see how much error we are getting. So, this is the observed value and this is the predicted value. By predicted value I mean I apply this equation for the given A and R and get the predicted value, and these are the errors. So, this is the type of error that I get if I use the expression that we just derived on the Q which is the peak discharge, and these are the kind of errors that we get. Then we go next and then look at the goodness of fit in some sense, that how good is this particular regression. So, we will obtain R square which is given by b dash x dash y minus n y cap square by y dash y minus n y cap y bar square. Y bar is the mean. So, in this case y bar is simply the mean of these values, observed dependent variable values. So, that is 0.672 and n in our case is 12 number of values. So, n y cap you can y bar you can get, and b dash we have obtained it, b we have obtained it as this vector 0.0351 etcetera, and b dash is the transpose of that. So, I write b dash as the transpose of that, and x dash y we have obtained earlier, and y dash y is simply y transpose into y, which comes out to be a scalar quantity which is 15.77. So, we know all of these values here, that is b dash is given, x dash y is given, you multiply these two you get 15.64, and when n y cap y bar square, so you will get 5.42 and so on. So, R square turns out to be 0.99. Remember R square, the closer to 1 the better is the fit. So, in this particular case a good linear fit exists between the peak discharge, the area of the watershed and the rainfall in the watershed. So, this is how we fit multiple linear regression equations. Typically these situations arise when we are dealing with number of variables. For example, rainfall in a particular location dependent on several climatic variables. For example, mean sea level pressure, it may depend on the geopotential height, it may depend on the land pressures, it may also depend on the wind speed and so on. So, when we are relating the hydrologic variables with climatic variables, which quite often arises when we are dealing with the climate change impacts, we need to relate the hydrologic variables with the climate variables. There are a large number of variables which are affecting the hydrologic variables when we start looking at the climatic variables, and therefore, we need to have statistical relationships between the hydrologic variables and the climate variables, and that is where we typically use the multiple linear regressions, and also some non-linear transforms also we use. Hopefully, in the towards the end of this course I will give some background on downscaling of climatic variables. In that lecture we will discuss how we use multiple linear regression for relating the rainfall in a particular location with the climatic variables and so on. So, these are the situations where we use the multiple linear regression, and this is the background for that, the way we obtain the parameters and the way we assess how good is a fit. Now, a question arises where we are dealing with a large number of variables in the multiple linear regression. Let us say P is quite large, let us say 10 variables, 15 variables, 20 variables etcetera, and then some of them may be correlated with each other. Let us say that one of the variables was soil moisture that you are using, and then another variable is evapotranspiration. Now, evapotranspiration and soil moisture cannot be treated as independent. The evapotranspiration is in fact dependent on the soil moisture, and then the more the evapotranspiration takes place, the more the depletion in the soil moisture. So, they are mutually dependent. So, if you are taking these kinds of variables where they are mutually dependent, there is a correlation that exists between existing between the two variables. and also you would not like to handle large sizes. What do I mean by that? Let us say you have 14 variables, 15 variables, and each of them have data for hundreds of years. Then the size that you have to deal with in the regression will be quite large. So, first to handle the dependence among the variables, and next to reduce the size of the problem, we devise certain methods and then make both these possible. And one of the methods that I will be discussing in the next lecture is the principal component analysis, which is a very powerful method for most of the multiple linear regression techniques, where you are interested in reducing the size as well as addressing the dependence among the several variables. So, in today's lecture essentially we saw how to obtain the rainfall hydrographs, starting with the IDF relationships. From the IDF relationships you obtain the intensity, and then we use the alternating block method to distribute this intensity across the duration. And then we went on to the next topic, which is the multiple linear regression. Starting with the linear regression, we have introduced several dependent variables in the linear regression expression, and saw a method by which we obtain the parameters beta 1, beta 2, beta p, etc., and also to obtain R square, which gives the goodness of the fit for this particular equation. So, in the next lecture we will continue this discussion on multiple linear regression and introduce the principal component analysis, by which we will address the dependence of several variables and also address the issue of the size of the problem itself. Can we reduce the size of the regression equations? So, thank you very much for your attention. We will continue the discussion next time.